Hello, everyone. Thanks again for joining us in this new series. Today, we're going to do diverging lenses. But before we delve into this, I would suggest that you review the introductory video that we did on thin lens terminology and sign convention, because that was the first in the converging lens series, but it applies to diverging lenses as well. Today we're gonna jump in and analyze the image of an object located outside the focal point of a diverging lens using ray tracing and the thin lens equation. And we're going to, in the next video, analyze the same, but with an object inside that focal point. I want to do exercises, okay? So before we begin, again, the usual, please like, subscribe, share on your social media, click that notification button, and comment on the videos that we make. And let's begin. So again, thin lens parameters, I'm going to go over them real quick. This is the shape that whenever we want to draw a diverging lens, we put it like this, okay? Different than a converging lens. These are the focal points. Obviously, this is the focal length right here. And some people draw it like this. They're both legit. We're going to stick with this, right? So here we need to know that the focal length is less than 0. For a diverging lens, the focal length is negative, okay? And thus the power is negative for a diverging lens. The object, whether it sits outside or inside the focal point, this is, object. The height is positive and the distance to the object is positive. However, the image of a diverging lens, the image of an object for a diverging lens, is always virtual. So di is less than 0. Hi is positive because it points up. Okay. And maybe now is a good time to just do a little, just to show you, using the virtual lab. Let's go to geometric optics. We talked about this at the end of the converging lens video series. So let's click over here and look at the lens. And right here, here's a diverging lens. And let's go to an arrow. And let's just see. Let's turn on the labels and get the principal rays in. We're going to talk about the rays in a minute. But let's look at the object. Let's sweep the object from all the way outside. This is the focal point. All the way outside the focal point. And let's sweep it in. As it comes in, as you can see, the image is still virtual, and it's getting larger and larger and larger. And here we hit the focal point, and nothing happens. And then we keep going in. The object is closer to the image now. The image is still virtual, and it's still shorter than the object. So for a diverging lens, the image is always virtual, no matter where the object is, okay? I want to see that in these two videos whenever we do the ray tracing, basically to just show this. For a converging lens, let's just review this here a little bit. Here's the object. As I come in towards the focal point, the image is real and inverted, okay? And as I come into the focal point, look at what's happening to the image, getting bigger and bigger and bigger, but farther away from the lens. And before you know it, when I hit the focal point, the image just vanishes. You cannot have an image, don't have an image anymore. And then as I move inside, the image starts to appear on the left right here. And I move it in some more, the image comes closer, but large and virtual, obviously, and upright. And it's on the other side of the object. See? For a diverging lens, the image is always between the lens and the object. For a converging lens, when I'm inside the focal point, the image is always to the left of the object, and it's virtual and it's upright. And when I'm outside, the image on the other side of the lens, inverted and real. Okay? So again, as you can see, it's always inside that the image is always inside that focal point, and it's always upright, and it's always virtual. All right, so that's good. So let's move on here to the rays. It's very important. So the first ray, still from the tip of our arrow, okay, goes parallel to the optical axis, but when it emerges, again, this is a diverging lens. So all the rays are gonna diverge, right? So what's gonna happen is the ray is gonna go away from the optical axis, but it has to go away in a certain way. The way it does it is it appears as if it's coming from the near focal point. So it appears as if it's, if you put your eye over here, you'll think this ray is coming from this point right here. And then it goes out. Okay? The ray going through the center will continue. This is the same as for the converging lens. But now the orange line, a ray directed at the far focal point. So it's as if it's coming through the far focal point, emerges parallel. Okay? So there's a little bit of difference in the ray tracing for the diverging lens. And now, as you can see right here, these three rays do not meet. So we have to project them backwards. And we do so. So here's the blue, here's the orange, and then the green still is on itself. And then here's our object right here. Sorry, this is the image. It is virtual, upright, similar to what we saw in the lab. Okay, so for this one, for this this problem, let's go ahead and look at the numbers. Let's see. So what we have right here is an object sitting at so let's see, 1 2 3 4 5 6 7 8 9 10. So let's take di, the image, so the object distance, sorry, do is the object distance, and let's take it to be 50 units, right? 1 2 3 4 5 6 7 8 9 10. And then the focal length is 1 2 3 4 5 6, so that's 30, but it's negative 30 units or negative 30 centimeters. You have to be careful. Whenever you're dealing with a diverging lens, the focal length is negative. Okay, and it looks like H sub O is 3 units. And from here, we see that DI is 1 2 3, so that's 15, roughly 17 and a half. So that's 20. So roughly 17.5 with a negative, because again, it is virtual. And its height, h sub I, is a little bit over 1, so maybe like 1.25. Something like maybe 1.1. All right. Well, let's see if we can now use the lens equation and try to get something, reasonable as compared to this. So let's go ahead now. And here's our lens equation, power and magnification computation. So again, lens equation. The same as before, 1 over f is 1 over di plus 1 over do. And remember now, f and di are less than 0. So let's just see where di lands, given what do and f are. So let's solve for di. So 1 over di equals 1 over f minus 1 over do. Same math as before. Nothing changes in the algebra. So here we have do times f over do minus f. And so flip them. Right? Let's plug some numbers in here. do was 50, f was negative 30. So here's 50 times negative 30 over 50 minus negative 30. All right? So this is, again, keep the numbers the same. Maybe we can simplify things. So here's the negative 50 times the 30 over, now this becomes plus, right? So 50 plus 30 is 80. So the zeros cancel out. So this is negative 50 times. So when I cancel this 0 with this 0, 3 over 8. So this is basically negative 150 over 8. Okay? So this is negative 150 over 8. And it's roughly negative 18.75. Okay? Units. So let's look at what we got. Again, actually, it's, I put here 17.5, but it's closer to 18. If you look at it carefully, if each of these is 5, 5, 10, 15, is 20. So it's closer to 20 than 15. So maybe it is 18 something. Again, with if you don't have a ruler and the rays are not exact, again, you're not going to get a good answer from the ray tracing, but I'll put you in the ballpark. Okay, so we are okay with the ray tracing. This is good. So now let's look at the magnification. So the power, what is the power? Power, again, is in diopters, and it's 1 over f. But f has to be in meters. So let's assume our units here are centimeters. Okay? So f was given to be negative 30 centimeters, which is negative 30 over 100 meters, or negative 3 over 10 meters. So the power is 1 over f, which is 1 over negative 3 over 10. You flip it, you flip the denominator because it's a fraction in the denominator. So you flip it and you multiply by the numerator. So you get negative 10 over 3 diopters. That is the power. And for a diverging lens, the power is given as negative. And the magnification, M, is negative di over do, and M for a diverging lens is always positive, because di is always negative, and negative times this negative is going to give you a positive. But also, this is given as hi over ho. Both of them are pointing up, so that both of them have the same sign. So M is always positive. Okay, so let's solve for hi in this case. So if we solve for hi just from these two right here, we cross multiply. Hi equals negative di times ho over do. What's that equal to? Negative di was 150 over 8, so negative 150 over, I'm going to leave it exact like this, times ho was 3 units over do, which was 50 units. The minuses cancel out. The 150 over 50 will give me a 3 times another 3 over 8. So this is 9 over 8, which is a little bit over 1. Okay? So let's see. 1.125 units. So we go back here. And again, this was like, again, I estimated 1.1. That's not bad. Okay, so this is good. So this is how we do ray tracing and thin lens equation for a diverging lens, the object sitting outside. That's how we draw the rays. Again, very important. A ray coming in parallel will appear to leave or diverge from the optical axis as if it came from the near focal point. A ray coming in, wanting to go through the far local point, is interrupted by the lens, and it leaves the lens parallel to the optical axis. A ray going through the vertex will continue going through the vertex, or the center of the lens. And these three rays do not meet on the other side of the lens, but if we project them backwards, they meet over here, okay? And it appears as the object is over here. Okay? All right. So next video, we're going to do the object inside. And hopefully you can join us for the other one. Thanks again. And hopefully we'll see you in the next video. Good night.